start AP Physics here because we only have less time than usual. That didn't make any sense, but okay. So last time we were talking about that new expression that we had for gravitational potential energy, which was negative capital G, the masses of the two objects divided by the separation between them. And you need to make sure that you remember that it's only r to the 1 and not r squared. You don't want to confuse it with FG, which is G big M little m over r squared. Okay, so just make sure that you got it right. Okay. And the chapter 12 homework was due yesterday, so I should be getting chapter 12 homework. Yes, you can. That's what I thought. Okay, but I need everybody else's. So let's just do an example problem that goes with this, and then we'll go back and talk about escape speed. Okay, so let's do page, I think it's page 381, number 38. If somebody would read it for us, please. Oh, of the book? Did you? Yeah, please do, because sometimes I like to be able to cut and paste things out of the book. That would be a big help. Don't do it right now, though, Priya. Right now, we gotta be doing class. Okay, so the key words here are that it's in deep space. So that's telling you that it's not near the surface of a planet. We don't have to worry about these objects being under the influence of the gravity from Earth or the sun or anything like that. The only interaction we need to worry about is between those two spheres. Okay, so we've got an x-axis. Goodness knows what an x-axis is doing out in deep space, but there it is. MA is sitting at the origin, which is where x is equal to 0. MB is hanging out here at x is 0.8 meters. We've got masses for these two objects. I think A is 20 kilograms and B is 10 kilograms. That sound right? Okay. And so I've got two particles, and we want to find what? The gravitational potential energy, which is, and remember the negative sign, negative G, MA, MB, divided by the R, which is the separation between those objects. And then it's just a matter of plugging in. I'm going to move down here to plug in so I have enough space. So I've got that negative 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times 20 kilograms times 10 kilograms, all divided by that 0.80 meters. And so what's UI going to be equal to? Thank you for remembering the negative sign out front. Did other people get that? Okay. So an important question here is, what are the units? Well, they should be joules, right, because it's energy. But my kilograms squared here are going to cancel with those kilograms. It is Newton meters, but what's a Newton meter? A joule. Okay, so it's always just nice to check and make sure that the units are what we expect them to be. And remember again that this is a property of the system of those two objects. When we're talking about gravitational potential energy like this, we don't have gravitational potential energy of a single object. It's always of a system. And even if we think about the old way, where UG is equal to MGH, it's still a property of the system. We just kind of gloss over the fact that the other object in the system is the Earth. Okay. So how about part B? What happens in part B? Okay, so we let B go, and it starts to move, and it moves 0.2 meters. And what's its x value now? No, 0.6. Okay, so what's happened to the potential energy? It decreases because the distance got smaller. But what happens to that energy? It turns into kinetic energy. Okay, so we could say that this gravitational potential energy that the system had when it was at rest and our initial situation has now become our total energy. And then we can figure out how that energy is split between potential energy and kinetic energy in our final situation. So this is initially where B was. This is finally where B is. And we're going to compare those two situations using total energy. Okay. Sure. Yeah. That's exactly what we're going to do. I'm going to start it kind of from first principles, which says that the energy in the initial state has to become the energy in the final state. And that I know initially I just have that gravitational potential energy that we already figured out. But afterwards, it's going to be U final plus K final. And K final is what I'm looking for. So I'm going to have U initial minus U final. And U initial was that negative 1.7 times 10 to the negative 8 joules minus negative, make sure you get all your negative signs in there, 6.67 times 10 to the negative 11th newtons, no, meters squared per kilogram squared times 20 kilograms times 10 kilograms, but now my separation is 0.6 meters, and that whole thing is going to be K final. You might want to calculate that out first. And then we can figure out what K final is going to be. Okay, good. And then remember, though, that you have two negative signs, and they're going to become a positive sign. And what are we going to get? Is it really 5.2? Yeah. Oh, okay. You had your other 2 in here. Okay. Okay. All right. So that was pretty much just a plug and chug. Okay. And then yesterday, we were talking about how in the Earth eraser system, that if I toss the eraser up, that potential energy that's stored in here gets converted to what? I'm sorry, that's backwards. The kinetic energy that I give it when I toss it up gets converted to what as the eraser goes up in the air? Potential energy. And the eraser goes up and it loses all of its kinetic energy and it stops, right? And then it comes back down. Free fall. But the whole thing is that I really want it to be able to leave the Earth. Okay, I want to give it enough kinetic energy that it goes high enough that it's not affected by the gravitational pull of the Earth anymore. Well, kind of. And so what we're trying to calculate here is escape speed. Okay, but we got to remember a couple things. Okay, so first of all, remember that this gravitational potential energy expression that we're using is always negative. Second of all, that gravitational potential energy gets smaller the farther the object gets from Earth. So again, I can talk about the total energy initially when that object is near Earth. And it's going to have some kinetic energy and some potential energy. And what's my expression for kinetic energy? Always. And my expression for the gravitational potential energy is negative G mm over r squared. Oh no, I'm sorry, over r. See, I made the mistake. Okay, whatever that r happens to be. So we're going to, when we talk about escape speed, we're going to talk about a very particular situation. And the situation is, as the object reaches infinity, it glides to a stop. So that when I'm talking about escape speed, I'm talking about giving the eraser enough speed when it leaves so that it can keep going, and just as it reaches infinity, it glides to a stop. Totally ridiculous, but there's a reason. So that means that my K final is equal to what? 0. And if my R is infinity, what's my U final? Also 0, right? Because when R gets really, really big, that UG gets really, really small. So what's my E total final equal to? 0. So what does my E total initial have to be? 0. Okay. So I can take this equation, which tells me that 1/2 m vi squared minus g big M little m over r is going to be equal to 0. And if I say that I am on the surface of the Earth, then I can solve for vi, which is going to become my escape speed. And you may think this is silly, but someday, when your spacecraft has crash landed on a planet and you need to figure out how you're going to get off after you fix it, it's kind of an alternate scenario. Because I don't necessarily need the mass and the radius of the planet. What I need is the acceleration due to gravity of the planet. And you can actually figure out the radius if you know a couple other things. Do a little astrodynamics, and you can figure out the radius just by looking at where the sun is at where the star is at different points of the day and measuring those angles. You might need to know, well, not necessarily, because they had a pretty good handle on the size of the Earth long before they knew how far away the sun was. Or, I'm sorry, long before they accurately knew how far away the sun was, because they screwed that up pretty good. Closer, because it's a game of angles. So you assume that you've got the Earth, the moon, and the sun, and you measure that angle. And so this is the configuration for a what? What kind of moon? It is a right, not a full moon. What is it, Maddie? Or third. I don't really care. It doesn't make a difference to me. It's a quarter moon. This is obviously something we'll have to, no, that has no. This is something we'll have to do after the AP exam. I can't let you go without knowing what the phases of the moon are. It doesn't matter. A quarter would have made me happy because I forget to. I have to stop and think about it. Okay, but anyway, they messed up this angle. This angle is extremely close to 90. It's like 89.8 or 89.9 or something. It's a really, really almost close to a right angle, and they made it too small. And so they messed up this distance. No, and that made them, and they messed up the two distances. It was Ptolemy. He did a whole bunch of wacky stuff. But you figure out the radius of the Earth by digging a really deep well so many whatevers apart, and then you have to, I guess you have to be crash landed with a friend, because you've got to have somebody at each position, and you measure, I'm sure we could figure it out if we wanted to, measure what happens to the sun. Like it has to go down those wells, and when it's directly overhead, and the time separation, and it's all this. And if because you would know if you knew the separation of the wells, and you knew how long it took for the planet to rotate, which you could figure out easily, then it's a game. You can do it. And really, if you crash landed on a planet, you've got plenty of time to do nothing but figure out how to get off. Okay, so that tells us that V escape, and again, of course, my little m's cancel, so it doesn't matter whether I'm trying to launch a Saturn V rocket or a mouse, which isn't entirely true, but yeah, they are. But it's equal to 0, so it doesn't matter. I can divide 0 by anything as long as it's not another 0. So that gives me the square root of g mm, there's a 2 in there, over re. And just for comparison, this part, remember yesterday, we decided was equal to that, I believe. So you don't really need the mass of the planet, you just need the acceleration due to gravity and the radius. Okay. I believe, I should have looked it up, I believe the escape speed for Earth is something like 11 kilometers per second. It's in the back of an astronomy book somewhere, but you could figure. It's 11, I'm pretty sure it's something like that. 11 kilometers per second. 11 kilometers per hour is nothing. You can walk practically 11 kilometers per hour. Well, there are all those problems with that, but okay. All right, so Kepler's laws, which maybe you remember from freshman year. Well, there's all kinds of other issues with propelling a human, an unprotected human, into space at 11 kilometers per second. And you could, and that person would, well, assuming also that you're isolated, so that it's not going to be shot anywhere near the moon, it's not going to go past Jupiter or Saturn or the sun and get caught in their gravitational pull. So it's a theoretical value. All right, so Kepler's laws, 1600s. Kepler was an apprentice and worked for Tycho Brahe. Tycho Brahe was drunk and took he drew diagrams of everything he saw at the sky, but he didn't do a very good job of analyzing them. So Kepler came along, took all of Brahe's data, and actually began to notice some things. Kepler's laws apply to all bodies orbiting each other due to gravitational forces. So it's Kepler's laws that help us make sure that, it helps us figure out where exoplanets are. It helps us figure out all of that stuff. And so I don't know what those masses are made out of, so when you leave here, I would wash your hands, because they may very well be lead. I mean, I have no problem with you touching them, but again, it's one of those, it never hurts to wash your hands. I would use soap, actually. Yeah, go right ahead. And you might have to like open it up. I don't know if I fixed the soap dispenser. See, I don't know if hand sand works on things like that, because it's killing germs, but it's not removing things from your hands. I mean, it is. You might have to open up the soap and pour it onto your hands. But I don't know what those, it wouldn't surprise me if they were lead weights. It depends on what kind of hand sanitizer you use. If you use, I think it's the alcohol-based ones, and if you use the alcohol-based ones, all they do is actually destroy that bacteria itself. It like breaks the cell walls or something, which is different than the kind that does, than the antibiotic kind, because that the germs can develop a resistance to, but the alcohol kind, it's just killing what's there. Orbiting each other due to gravitational forces. Okay. And he came up with 3 of them. They were developed for the solar system, so they're a little, well, solar system centric. So the first one is the law of orbits. And this one's pretty easy and pretty straightforward, and it basically says all planets move in elliptical orbits with the sun at one focus. Okay, so usually when I do this, here's my ellipse. Remember that an ellipse has 2 important axes. It's got an axis this way and an axis this way. In astronomy, well, we're going to be concerned about the long one, which is called what? Yeah, sort of. That's the major axis. This one's going to be the minor axis. Half of the major axis is what we call A, which is actually all we care about in astronomy. An ellipse has two foci. Anybody remember the purpose of the focus of an ellipse? The purpose of the focus of an ellipse is that if I add the distance, if I take any point on the rim of the ellipse, okay, and I add the distance from focus to ellipse, from focus to the point and from the point to the other focus, that distance, the sum of those two distances is the same for every point on the ellipse. So if you ever need to make an ellipse, you take a piece of string, you thumbtack down the two ends, draw your pencil so that it's taut, and you draw the ellipse that way. A font of useless knowledge. Okay, so the planet goes around the outside, and the sun is there. What's really happening, which we figured out later, is that the two objects actually orbit in ellipses around each other, and their foci overlap at the center of mass. The center of mass of the solar system. And it does that tiny little bit of a wobble because the sun is so massive that the center of mass of the solar system is very close to the center of the sun because it is the most massive object in our solar system by far. So it looked like this to Kepler, but then when we got better telescopes and we were looking out into space and we were looking at binary stars that were orbiting each other, you could tell that they were actually both moving in ellipses around the center of mass, and the center of mass was where the foci of each of their ellipses overlapped. No, 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 no. Everything in our solar system, with the massive things in our solar system, have stable orbits that are very well documented and studied. The little things like comets and asteroids and meteoroids and maybe some of the dwarf planets, we don't understand those as well, and because they're so small, they are more easily influenced by things like Jupiter. But there is an argument that the reason that life was able to arise on Earth is because Jupiter cleared out all of the debris. And if we didn't have that massive planet that ejected all the little crap out of the inner solar system, then the Earth would have been bombarded by too many asteroids and meteoroids, and it wouldn't have been a stable enough environment for life to evolve. So there's a question of, no. Yeah, but it's for a reason. I mean, all right, so Kepler's second law, which is the law of orbits. What? Oh, sorry, law of areas. It has to do with orbits. Thank you. Okay. So this one says a line that connects a planet to the sun sweeps out equal areas in equal areas in the plane of the planet's orbit in equal times. That is the rate dAdt at which it sweeps out area A is constant. A line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal times. That is, the rate dAdt at which it sweeps out area A is constant. We'll talk in a minute how this is basically a statement of conservation of angular momentum. But you kind of got to visualize it first. Okay? Okay, everybody got it written down? All right. So, here's my orbit-ish. Like that one. Should be an oval. It's actually an ellipse. Okay? So here's my semi-major axis. Here's my minor axis. Here's going to be the sun. Okay? So, what this is saying is when the planet moves from here to here, and it takes some time dt or delta t for the planet to move, that this line sweeps out this area, which looks like a short fat triangle. Okay. But every time the planet moves through time dt or delta t, it has to sweep out the same area. So when the planet is down here really far away, when it moves through dt or delta t, this area has to be the same as this area. And so you can kind of see how I can fold up this triangle on itself, and it would take up the space of this triangle. So I can either have a long, skinny triangle or a short, fat triangle, but they have to have the same area. but it has to be in the same amount of time. That's the thing. And this is most dramatic, which is why I choose these. I mean, as I go from here to here, it's got to be the same area. Okay? So my question for you then, and just in case it ever comes up on a trivia game that you play, this is apogee. Yep. And this is perigee, just in case. Where is the object, the planet, going to move the fastest? And where is it going to move the slowest? Yeah, it's got to move fastest here. And it's going to move the slowest over here. Because over here, it's got to move a much larger distance in delta t than it does when it's very far away. And hopefully, this will be a good enough YouTube video after we skip the ad. And it'll just show me what I want to show. Whatever. Yeah. Oh, Kepler's second law. You can actually see how it kind of speeds up and slows down as it goes around. But I was hoping this would be one that had a okay, so you can see, hopefully, that here we have, she's saying it takes 1 day to travel that distance. You can't hear her, I can. But that this is a short, fat triangle, and this is a much longer, skinnier triangle. Okay? Hers isn't as... Okay? But that's what it has to be. Okay, so it's got to move faster over here because it has a longer arc to make around the sun than it does over here. Okay, so like I said, this is a statement of conservation of angular momentum. So remember that we figured out that tau was equal to dl dt. Okay, but what's tau equal to? Okay, r cross f, rf sine phi. Okay. And remember, what's f equal to in this situation? Kepler's laws apply to all objects that orbit each other due to... Well, it's not, no, it's not ma. It's a specific force. It is Fg, and in this case, Fg is equal to what? Okay, that Fg, because I'm talking about objects that are very far away from each other. Okay, and they appear like point masses. I'm not dropping a planet near the surface of the Earth. I'm talking about a planet and the sun orbiting each other. Okay, so as we move away from the sun, when we're over there at apogee, far away, when r gets big, the f is going to get small, but the r is going to increase. But if I substitute in here, and I don't even care what sine phi is. Nobody does. It doesn't matter. okay? Then that r is going to cancel with one of those r's, and that means that I can say that tau is proportional to 1 over r. So as r increases, as we move far away from the planet, what's going to happen to tau? It's going to decrease, which means what happens to the change in momentum? Well, not necessarily. If tau is decreasing, what has to happen to dl dt? That has to decrease too. Okay. And how do I write L? In a situation like this where I'm talking about point masses that are pretty far away. I omega. So if L is decreasing because this is decreasing, what's happening to omega? Omega is going to decrease too. So that tells you that when the object is far away from the planet, the omega is going to decrease and it's going to move slower, which is exactly what we saw. Okay? I don't know if you necessarily need all of this, but it's just a way, once again, to see that everything is consistent. Okay? All right. So, Kepler's third law, the one with the equation. The law of periods. So the law of periods says the square of the period, it's actually the sidereal period, but it doesn't matter, of any planet is proportional to the cube of the semi-major axis of its orbit. So effectively what we're saying here is that t squared is proportional to a cubed. Tend to be the same. So it's all a context thing. So because this is AP Physics, we're actually going to look at this and figure out how those are related, what that constant of proportionality is. In astronomy, I don't make people do that. And Gianni's not here. I've already taught all of this to Gianni. I could have she could have been helping me along here. All right, so we are, doesn't really say that there. It's upsetting to all of us that Gianni is gone. All right, so I'm going to kind of switch around my axis system a little bit. So here's going to be some big mass, which is going to be my star. I'm going to have a planet out here, and to make my life easier, it's going to move in a circular orbit, which is okay. Because honestly, most of the planets move in orbits with eccentricities very close to 1. Okay, so the only force acting on my little m planet is the gravitational force from with big M. And they're going to be separated by some distance r. And if I want to make this into an ellipse, I can. It just makes the math a little more complicated, but it'll work. And because my little planet here is moving around in a circle, what kind of motion is it undergoing? Yeah, but things moving around in circles that are drawn to the thing in the middle is a certain kind of motion from a long time ago. No. It's exactly like if I had something attached to a string and I was spinning it over my head. What do we call that? Centripetal motion? Centripetal. Uniform circular is the word I use sometimes. Okay, so this, and this isn't necessarily uniform circular motion if we turned it into an ellipse, but it is centripetal motion, which means that we can say that F net is equal to MAC. And I just said that the only force acting on it is that force due to gravity. And so that's going to be G big M little m over R squared. And because I know that I eventually want to work the period into this, I want to express AC, the centripetal acceleration, in terms of omega. What's that? Sure. Yes, so? I know, hang on, let Priya figure it out. Is she right, Zoe? Oh, okay, so it's just going to give us omega squared R. I can cancel my little m's. And then I'm going to say, what? No, I can't cancel it. And then I'm going to remember that omega is what in terms of period? Okay, so I can substitute in here. So I'm going to have G capital M over R squared is going to be 4 pi squared over T squared times R. Well, remember I said that T squared and R cubed were proportional to each other. So what I'm going to do is I'm going to bring this R over here for starters. So I'm going to have GM over R cubed is going to be 4 pi squared over T squared. And then I'm going to write it 2 different ways. I'm going to write it as T squared over R cubed is equal to 4 pi squared over GM. Make sure you can follow that algebra. And then I'm also going to write this as t squared is equal to 4 pi squared over gm times r cubed. But I'm going to wave my hands a little bit. I forgot my wand. And make that a cubed for the semi-major axis. And I can wave my hands a little bit because what I can really do is take each point kind of separately and make it work. Or I can make it work at the point at A, actually is what I can do. I should let R be equal to A. So that's it. This is Kepler's third law. But I want to go back to the way I wrote it first. Which tells you that that ratio of t squared over a cubed is equal to a bunch of things that are constant. 4 pi squared and g are the same everywhere and for always. And m, in this case, we could say, would be the mass of the sun. Which means that t squared over r cubed is equal to the same thing for every object that orbits our sun. So that I can say that t earth cubed squared divided by, and we'll turn that into an a earth cubed is going to be equal to t squared Jupiter divided by a Jupiter cubed is going to be equal to t Mars squared over a Mars cubed. Etc., etc., for any asteroid, comet, meteoroid, planet that orbits the sun. And you may ask yourself, why do I care? What's the period of the Earth's motion around the sun? In astronomy, we really like the number 1. I will bend over backwards in astronomy to pick units so that I end up with a 1. Here's where we really miss Gianni. What's the semi-major axis of the Earth's axis? Or the mean distance between the sun and the Earth? Anybody know? Try Googling mean distance between sun and Earth. It's a definition for something. Well, the mean distance between the sun and the Earth is what's called an astronomical unit. And it's something like 1.5 times 10 to the 8th meters, maybe? That can't be right. It might be 1.5 times 10 to the 11th meters. That could be right. That sounds better. Okay. But the bottom line is, what's 1 squared divided by 1 cubed? So now if I take something like t Jupiter squared divided by a Jupiter cubed, that has to be equal to 1. So for instance, I happen to know, because I'm me, that Jupiter is 5.2 AU from the sun. So can you tell me how long it takes Jupiter to go around the sun? No, no, that sounds about right. You take 5.2 cubed and then you take the square root. Okay, so I can do that for anything. Pluto is 39 AU from the sun. Okay, or you can measure how long it takes an object to go around the sun, which is probably a little easier to measure, and now you know how far away it is. So it's a pretty cool thing. I mean, this is nice and you need to know this, but the fact that you can choose the units appropriately and now you can figure out either the orbital period or the astronaut or the semi-major axis of anything orbiting the sun, if you know the other, is pretty cool too. All right, the bell is going to ring. I really